Hello, everyone, and welcome to this workshop on MLOps without much ops, presented by our guest speaker, Jacopo Tagliabue. Jacopo was educated in several acronyms across the globe, including UNISR, SFI, and MIT. He was co-founder and CTO of Tooso, an AI company in San Francisco acquired by Coveo in 2019. Jacopo is currently the lead AI scientist at Coveo, shipping models to hundreds of customers and millions of users. When not busy building products, he's exploring research topics at the intersection of language, reasoning, and learning. He is a committee member for international NLP IR workshops, and his work is often featured in the general press and AI venues. In previous lives, he managed to get a Ph.D., do sciencey things for a pro basketball team, and simulate a pre-Columbian civilization. My name is Juan Carrillo. I am a volunteer at TMLS, and just before we begin, if you have any questions, please ask them in the chat with a Q in the front so that the facilitator can identify them. And lastly, if you have purchased a summit ticket and are joining us for the talks on November 17 and 18, please take a look for an email from Hopin in your inbox today or early tomorrow for you to join the platform. Thank you very much for joining. And Jacopo, please take it away.
Hi guys, thanks so much for the nice intro. Hi everybody, thanks so much for taking the time to be with us today. I shared a link into the chat. Hopefully everybody sees this. It's a link to this repo here, which we're gonna get later today. But yes, I just wanted to share it so in case you want to, make sure you can reach the repo, clone it, go through it while we talk through and so on and so forth. So we're gonna go through that in the second phase. So the plan for today is, so we have some time to spend together. So the plan for today is we're gonna have a first section, which is more conceptual, as in we're gonna explain a bit what we mean by MLOps without much ops. We're gonna introduce the problem and we're gonna kind of give an overview of what we feel is a good framework to think about MLOps in practice. And then in the second part, we're gonna do a small pause so that everybody can get a coffee or some water. And then we're gonna get a more hands-on session when we're actually gonna look and see at actual code, actual tools, actual repo, how this principle can be operationalized in practice. I strongly suggest everybody to ask questions during, my presentation, as in, if it should be more of a dialogue than a lecture. If I don't see the chat message because, I don't know, Zoom is not collaborating or something like that, you can also unmute yourself and ask questions. I don't really mind. Okay, so please ask away anything that you don't find clear, or or ask any clarification questions if you have doubts that what I'm saying is applying to your use case as well. So let's start very quickly, since I already got a nice introduction, but about me. So I was the co-founder and CTO of a company in Silicon Valley called Tooso. I'm the handsome one in the picture. Tooso was building NLP and information retrieval API, mostly for big retailers. The company started in 2019, so that was the plan. And sorry, 2017, it was acquired in July 2019 by Coveo. Since this is the Toronto Summit, you probably know Coveo. Coveo is Canadian originally, unicorn doing ML and AI for several use cases. And Coveo acquired Tooso in 2019, and I've been at Coveo, leading AI since then, and I'm now director of AI at the company. What does it mean to do AI at Coveo? If you have been to one of these conferences the last couple of years, you already have the misfortune probably of hearing my Italian accent and voice several times. The AI team at Coveo is very active in the community, and we collaborate with tons of other institutions, either universities like Tilburg, Queen Mary, Stanford, Bocconi, and so on, and also other organizations. For example, we work with people from Uber, people from Microsoft, and other companies as well. And this is just a sample of the publication that we had in the past and a sample of the papers that you can find if you're interested in what we're doing. There's a new page in our website. It's called research.coveo.com. I strongly suggest you guys visit that. It collects all of our publication, all of our talks, and all of our open source contribution. Last year, we got about 15 minutes of celebrity when we won the best paper award in NAACL, one of the top NLP companies. So going back to our main point. So we won best industry paper award last year at SIGIR, and we open source the biggest e-commerce data set like probably in history. Was part of the SIGIR data challenge last year with team from Rakuten, NVIDIA, and so on and so forth. So we're very active in the community from a research and open source point of view, as we really believe not just in open sourcing our ideas or sharing our ideas to papers, but also open sourcing data and code so that people can actually advance the state of the field together. For those of you who do not know about Coveo in detail as a business, not just as as a famous Canadian company. So Coveo raised more than $300 million in the last 3 years, and is a hugely growing startup in the AI ecosystem. Coveo mostly provides services to 4 lines of business, so website, workplace, customer support, and e-commerce. He has more than 500 customers around the globe and more than 1,000 deployments. What we're gonna say today, hopefully, is inspiring for all sorts of companies, but especially for companies like us that live and breathe data, AI, and machine learning models. So done with the intro section. We're not gonna talk much about research. I know like a lot of the things we said in the intro were about like papers and stuff. But today we're actually gonna talk about a very, very practical thing, which is what happens once you write a paper, once you have an idea on machine learning. How do you actually make sure that your ideas and your models and your fantastic project actually make it into the way to production and make an impact in the real world? And these kind of like tools have been known in the recent literature with the name MLOps, which is kind of an umbrella term for everything that relates to the fact that machine learning system are slightly different than software system. And so they kind of need a special care when you try and go from a prototype that works on your laptop, let's say a Jupyter notebook, to something that actually runs at scale with hundreds of millions of final user, like for example, Coveo models. So why do we even need to discuss this? So as you're probably aware, this whole AI renaissance, after some decades of AI winter, started when people realizes that there's a lot of cool statistical stuff that we can do, in particular with deep learning, and at a given scale. So big tech like Google, Facebook, and so on and so forth started open sourcing frameworks and kind of evangelize the field that if you have a lot of data and you know what you're doing, there's a lot you can get out of machine learning. Everybody gets excited about ML, and and a lot of people started debating about what happens when you deploy ML system in the real world. But the truth is that outside of very few players, which of course have no problem in getting value out of ML system, most people still haven't figured out how to actually deploy ML and runs it in production. If you're like me, you get things like this one from Gartner in your inbox / LinkedIn feed literally every day, right? Which it turns out that many people never go out of prototype hell, like never got out of a phase when some machine learning stuff happening on somebody's computer, but then it's also impossible to make them work at organizational scale. This is a stat that should be worrying in that respect. So this was the original marketing slide, so I'm sorry about the marketing flavor, but this is not the point of this slide here. So this is a count of how many publications in e-commerce track at elite conferences happened in 2020 by industry player. What you see here is that everybody in this slide, except one Canadian player, is an immensely big corporation, mostly American or Chinese. And there's no other player in this space that is doing cutting edge ML, in this case for e-commerce, which is mostly my use cases, aside of this, few players. Well, again, this looks like a marketing slide, but actually it's a terrible slide for the field if you think about it. It means that everything we do as a cutting edge ML, everything the community is talking about, is kind of shaped by the agenda of retailers and of companies that are not like anybody else. Like Amazon has problems, but also resources that nobody else has. So of course, it's super exciting and inspiring to watch what Amazon researchers do, but also the chances that applies to other people in the same industry, even just in the same industry, is actually very slim. It's like if we're all trying to, learn how to play tennis, and the only thing we find online, the only thing we discuss as a community is, Roger Federer training routine. The truth of the matter is that while it's awesome to watch Roger Federer training and it's very inspiring and it's super useful to know what the best of us do, none of us is Roger Federer. None of us is Roger Federer now because we're actually trying to learn how to play tennis. And very few of us will even become professional players in 10 years from now. So we have an entire field where the only thing we look at is Roger Federer training skills. But all of us, or most of us, are actually just learning how to, kind of handle a racket. And that's kind of the field of ML as we discuss these days, which is a pity. So today, it's all about what you can do with ML and AI and what we call the reasonable scale. So forget about these giants that have opportunities and challenges and a resource that nobody else has. What everybody else can do to be on this map next year. Like if we redraw this map next year, how many companies that are not, humongous multi-billion-dollar businesses will contribute to ML next year? And how can we make them so? And today is a message of hope. Today I'm going to show you that there's, there's some reason why that chart looks like that, but it doesn't need to be like that. There's a lot of hope for companies at reasonable scale. So what is the reasonable scale that we kind of like, floating around as a catchy phrase? So reasonable scale is kind of like jazz. Like it's very hard to define exactly what it is, but there are some features, some flavor, some type of. By the way, if you're really interested in this, there's a fantastic Towards Data Science series that you can actually read. That is the link. So on the computing side, a company that is reasonable scale will have a finite amount of computing budget, not infinite amount. Like, for example, let's say Coveo. Coveo is a company reasonable scale. Like we have a lot of clients, we have a lot of data, and we have a lot of GPUs running at all time. But of course, compared to Amazon, another company in the chart that you saw before, we don't have a cloud provider from ourselves. Like we do not own AWS. So while there's a lot of things we can do, there's still a limited amount of computation we can use. That is the team size. Like, reasonable scale companies have dozens of, ML engineers, but they have not hundreds or thousands of engineers. There's the ROI point of ML project, right? Where reasonable scale companies can deploy, let's say, a new recommender system or, a new prediction for, house prices. And maybe they can get $1 million out of it, dozens of millions of dollars out of it, but certainly not billions of dollars out of it. In other words, the marginal value of better models for reasonable scale is in the millions, not in the billions. Again, if you want a comparison, remember the difference between Coveo and Amazon. Like Amazon recommender system, if it improved by 0.5%, is going to actually make billions of dollars because at that scale, marginal improvements matter so much. And finally, data. Of course, reasonable scale companies that are serious AI players like we are have a lot of data, terabytes and terabytes of data, but it doesn't compare with the petabytes of data a day that Uber, for example, collects. So of course, these dimensions are all correlated with one another. And some companies may be reasonable size for one of these features, may not be reasonable size for some of the other feature, but altogether, they kind of depict, like a profile of a company that hopefully it's pretty clear to all of you. And the most important thing is that the vast majority of companies doing ML right now, trying to actually make ML work, are reasonable scale companies. So look at this chart here when we kind of, depict the landscape in front of us according to two dimensions, scale and how proficient the company is at ML, right? So on the left side, left top, you're gonna have late adopters. And these are people that they need help with productionizing ML tool. These may be companies that are not reasonable scale in their own business. I don't know, Pfizer or Procter & Gamble or whatever. So this may be super gigantic company, but whose primary business is not a digital business. So as far as digital business is concerned, they're actually reasonable scale because it's the first time that this company tried to adopt, machine learning and AI in their own ecosystem. On the top right, they're the leaders, the people that we mentioned before, the Amazon, the Alibaba, the Google of this world. And they surely don't need our help in productionizing ML because they actually pioneered the field. On the bottom right, we have small animals. If we want to stick with e-commerce industry, we can consider, a small shop on Shopify. These people have maybe 2,000 items and have way, more basic problems than ML now. One day they will grow to have ML problems, but right now they don't need help with ML. They need help with platform, payment, logistics, and so on and so forth. And finally, on the bottom right, we have early adopters. These are people that are very sophisticated, but maybe they run a startup with 20 people, and a Series B funding. So while they really know what they're doing, they need a reasonable scale, kind of like out of necessity, because they're constrained in the amount of money and the amount of people they can throw to the problem. And as you can see here, this is the red, the red area. This kind of this overlapping area where we can help people at reasonable scale being productive with ML. And we know because we're a reasonable scale companies ourselves, right? So we became a unicorn while being a reasonable scale company. And so we're super thrilled and happy and excited to share with the community what we learned by doing this at a pretty significant level. So why our ranking, like the ranking that we showed before, was basically full of companies that are big data companies, and there was only one reasonable size company there. So there are many barriers to entry when a reasonable size company wants to do ML. Either productionize ML or ML research. Typically these two things tend to go hand in hand. As in, companies very sophisticated ML research tend to be also pretty good at MLOps and vice versa. But this is not necessarily the case. So we identify 4 main problems that engineering, like shipping ML model to production, is actually very hard. And big data companies can deploy very complex model pipelines because they're pioneering this and because they're they perfected the art of ML at scale. There's a problem of computing, which we touched upon before, which is, of course, big data companies do not have much constraints in terms of how many GPUs they can have, or how large of a data set they can use to train stuff. There's a talent constraint. As in, big data companies, of course, can attract the most talented machine learning engineers out there. So if you're thinking of doing cutting edge ML, for Google and Amazon, it's much easier to attract people that are naturally, more attracted to that side of work because of the compensation and the scale that they can offer. And finally, even constrained ourselves to pure machine learning, there are at least 2 problems with the current field for a reasonable size company. Problem number 1, a lot of the models we learn from in the literature are really not representative of what people at reasonable size see every day. So there's a premium in the literature to deploy super complex model, let's say a YouTube recommender system, which again is like Federer training. It's very inspiring, but it doesn't really tell much to people that works outside of YouTube, at a very different scale. So it's very hard for practitioners at reasonable scale to find something that they can take away from, top conferences and apply to everyday, to their everyday life. The second problem is that data sets that we use very, very rarely capture the properties of average deployments. There's a famous example from Rakuten a couple of years ago in SIGIR. It's a paper we know very well. We're gonna meet the same paper, down the line today, and it's a paper about intent prediction. So it's a paper that is about detecting if a shopper browsing on a website is gonna buy something at the end of the session or not. Like the standard e-commerce problem. And when you find out, when you read the paper and you read the data set that the model was trained on, you find out that the conversion rate of Rakuten in that data set was 25%, meaning that approximately 1 out of 4 people in the website actually ends up buying at the end of the session. And so the model that they train and all the paper and all the story is about how they're able to predict which one of these 1 out of 4 person is actually going to buy. The funny thing is that if you go out of Rakuten and you go into real e-commerce, that number is not 25%. The number may be anything from 0.8, 0.9 to 5%, which now means, if you know machine learning, that the imbalance between the two classes is way, way, way more severe than what the literature actually will lead you to believe. And so there's nothing wrong with the problem itself. There's nothing wrong with how we frame the problem itself. And of course, it's an interesting problem for everybody in term prediction. But the chances that a Rakuten dataset will actually be representative of what people find in their everyday life is actually really not, an accurate description. So these are all problems that people at reasonable scale need to overcome to be able to do ML and MLOps, and at a cutting edge level. Unfortunately, while we're very opinionated about all of this topic, so I'm happy to discuss more about any of this. But today we're just going to focus on solving the first problem, because we do not think that it's true anymore that only big data companies can deploy complex model pipelines. We believe that every company, irrespective of its size and its sophistication, can deploy model pipelines today effectively, and so can be part of this community. So this is a message of hope. If there's anything else you need to take away from this talk today, is we say you really do not need a bigger boat. Irrespective of how small is your team, how constrained you are, there's a way to make ML pipelines work at scale, thanks to the incredible community of open source MLOps tool that we have at our disposal. So it's true, the reasonable scale makes a lot of things harder. So there's a lot of constraints, like, there's not enough GPUs, not enough people, data set sucks, and so on and so forth. True. But remember, the reasonable scale also makes a lot of things easier. And this is an opportunity, because since we're operating at reasonable scale, there's a lot of things that you can just buy, or in the case of open source downloads, that have acceptable performances for what you're trying to build. In other words, at reasonable scale, you can build a lot more with less, if you know which products and which tools to use. And today we're going to talk all in details about which products and which tools work for us that actually will make your life easier as well. So let's look at what we found as the 4 principles of reasonable scale companies. And hopefully most of you here are working for a reasonable scale company as well. So we have 4 principles, and we're going to see how these 4 principles actually get operationalized in practice today. But it's very important to have this somehow top-down approach to make sure that we're covering all the bases here when we think about a data pipeline for a reasonable size company. So the first thing is the importance of data. Sometimes this is called data-centric AI. It's been recently popularized by Andrew Yang. But there's a general belief in the community, and this is becoming more and more important, is that the biggest marginal gain when you build MLOps system is that data always comes first. So the biggest marginal gain is always in getting cleaner data, better data, more accessible data, and so on and so forth. This is way more important than small modeling adjustment. In other terms, modeling is becoming commoditized. You may have heard of AutoML or low-code solution, and so on and so forth, especially in fields like NLP or vision, where large pre-trained models are kind of half of the job, right? So a lot of contemporary NLP is, downloading a model that somebody else trained on, a huge corpus, and then you fine tune it to your use cases, and then you build a classifier on top of it or something like that, right? So the bigger marginal gain is always in the data. Principle number 2, a clear separation between data ingestion and processing produces, replayable and reproducible pipelines. What this means, and we're going to see it with an example later, is that we really need to take a great care in making sure that we store all the data that comes into our system in as a raw and unedited format as possible. And then we need to have a version and replayable system that goes from those raw data to feature aggregation, whatever we need for data analysis and ML. Okay, this is important because you can make mistakes in building data pipelines. And by keeping this separation clear, and by keeping sure that we always keep a record of what was the state of the system in a raw sense when things happened, make sure that you can sleep, you can sleep soundly at night. you know that if you made a mistake in aggregating data, for example, you can always go back to the original data, delete all the transformation and somehow replay all the data to the system and get this kind of like a, stateless feeling of, repumping all the data, to downstream system in a way that makes sense. Third point, PaaS and FaaS is better than YaaS. So when resources are limited, our belief is that we should always focus on what matters. And if you're building a data company or an AI company, an ML company, whatever, infrastructure is really not, your core value. Like the valuation of your company or, your revenues or whatever metrics you're going to use for success is not going to be tied on how well you run a Kubernetes cluster. It's not going to be tied to how well you run a EMR cluster with Spark. It's going to be tied by, how much you can do, in your own field, which is, building better recommender system or building a more scalable, house prediction pipeline and so on and so forth. So if resources are limited, which by definition, reasonable companies, which because it's true as reasonable companies, adopting fully managed services to run computation for you is a very, very, very sound investment of our money, because people cost way more than computing. And people get really annoyed when their entire job is to kind of build infrastructure or replace infrastructure that somebody else built better. So this may be contentious, but at the end of the day, spending more in infrastructure is typically way better at reasonable scale than spending more in people, because infrastructure scales in a much more predictable way than actual people do. There are some questions. One second. Oh, sorry. What does PaaS mean? Oh, thanks so much for answering. Yeah, sorry. PaaS means platform as a service. PaaS means function as a service. If you're familiar with AWS Lambda, that's function as a service. And YaaS is infrastructure as a service. Finally, vertical should be preferred to distributed computing when possible. My first company, Tooso, was built entirely on a distributed computer framework that you may know. It's called Spark. In particular, we're using a hosted version of Spark on EMR for AWS. It obviously did the job that it was supposed to do at the end. But then Snowflake came along, and it kind of transformed the way in which we're thinking about this. As in, Snowflake finally gives people this feeling of running a query while abstracting away all the distributing part. And on me, the receiving end of this query, there's no more distributed computing that needs to happen, because once data is taken out from Snowflake in a properly formatted way, everything else can kind of run in a vertical design, which is way more efficient than distributed computing. Distributed computing was very important for the big data revolution, but it also forces people to learn new ways of coding. Like Spark forces data scientists to learn different ways of like running stuff. It's very slow. So this continuous feedback loop that is very important when iterating on machine learning project kind of get lost, because Spark is kind of like a bit clunky. And also it's very hard to debug and to maintain, right? Like debugging and maintaining Spark is actually a job for a team. And we strongly suggest to not do that anymore at a reasonable scale, because there's a lot of better tools that will abstract away all that distributed complexity and will give you back all the time and all that simplicity that you can use, again, to improve the value of your company and not to manage infrastructure that at the end of the day, is just a means to an end. So it's really a fantastic moment to be in machine learning, mostly because you don't have to do much. Everything we just said, all the principle we just announced, all the code we will discuss in this an hour and a half together, can allow you to solve this problem very proficiently, without basically write any line of code yourself. We have now solution for model serving. We have data warehouses, as we discussed. We have solution for data transformation, low training, low codes, ML. We have solution for ML pipeline, for orchestration, for visualization. All of this was not true 5 years ago. When I built my first company, almost none of this was there. And part of this evangelization effort that we're doing to other companies at reasonable scale is somehow answering this question. if I had to rebuild a data company now, in the same sense that I built Tooso in 2017, which choices would I make? And it's striking, and I think it's a testament of how incredible is the ML and the MLOps community these days, that none of the choices that I made 5 years ago will actually be still made today. Because the ecosystem is so rich in so much better tools, there are way better ways of enforcing the same principle that I announced in a modern data stack. So while obviously, we will discuss tools today, and we will say that we like this tool over that tool, or that we suggest X over Y. Obviously, there's room for for disagreement. Like, we can disagree over which tool is better at doing something, or there may some be affinities with existing problems that make one tool better than the other for you, but not for me. But generally speaking, what matters are principles and functionalities. So the general lessons by shipping models to hundreds of millions of people for us has been that ML system is a combination of two things, and they are equally important. One is data pipeline, one is data, and the other is models. You can't understand the behavior of a production system without understanding both of this, okay? And what does it mean? Well, it means that on data pipeline, you need to understand, or need to operationalize all these roles: ingesting data, transforming data, checking the quality of data. On the pipeline side, you need to operationalize, preparing feature, starting from the data that you clean and validate. You need to run experiments, and then you need, when applicable, to do, some tuning for your models. And finally, once you ship data and models, into a production system, you will need to scale, the predictions and make sure that the system is reliably working at scale. And then, of course, you need to monitor the prediction to make sure that the system actually does what it's supposed to do. Okay. If you are in the very lucky position of thinking for the first time, you have a clean slate, you are building your ML backend from scratch today, these are the pieces recipe to fill these pieces of the puzzle with actual tool and code that works at scale. And you can use our recipes, completely open source if you want, but you can also make modification depending on your use cases and your preference. But at the end of the day, if you're building from scratch a machine learning pipeline and you want it to work at scale, this is what you need to do. There's no way around it, okay? So please, bear this in mind if you're building this today. So let's break it up in two parts, like data first and ML pipeline. We're gonna go a bit faster on these slides, as we're gonna share the slides afterwards. So there's a lot of references here, and you can just go through these references, a link by yourself, but I want to leave some time for coding and discussion at the end. So let's start with a simple example to understand like a very, very common pattern that we're seeing in data ingestion and in data engineering. So let's say we're building a recommendation system. I mean, sorry for the e-commerce example again, but I think e-commerce is easy enough that even if you don't work in e-commerce, you can quickly understand what this is about. It's a very easy use case. So recommender system work by ingesting catalog data, like let's say a list of product of, I don't know, Nike, Adidas, Mizuno, whatever, and then ingesting some data about what people purchase, right? And a recommender system is a model trained on catalog data and behavioral data that gives recommendation to new shoppers of what they should buy. Everybody, every time you shop on Amazon, you interact with 1,000 recommender systems at once, okay? So imagine building this data pipeline, right? So this data pipeline is ingesting a catalog at T1. Let's say today we ingest a catalog. A catalog, on the left here, it is basically a table that tells you for which SKU. SKU is the technical term for product ID. So for which product we have, which metadata. In this case, we have a product which is called 123, which is Nike shoes, whatever, and it costs $112. And we have a product which is called 8676, which instead is a pair of Adidas shoes and is 145. Okay, and hopefully all these are going well. And then a day goes by, and now it's T2. Now it's tomorrow. Let's say now it's Tuesday, and now the merchant that wants us to build a recommender system send us the updated catalog. The updated catalog contains the same product that it contained before, but now there's new prices. For example, the prices of SKU 123 is now $132 US. Okay. So what we do, which is the most natural thing to do, is that, well, we have a representation of the products, which is, the table that we have here in T1, okay? And we update it with the new information at T2, right? This should be fairly naive and uncontroversial. So we have a representation of a product, new information comes in, and we update it, okay? That should be what everybody should think of doing, right? Okay, this is wrong. This is profoundly wrong. And hopefully I'm gonna be able to explain to you today why this is really a bad pattern. I know that this is the more common one and it kind of makes sense from some perspective, but it's really, really, really an anti-pattern when you think about building data companies. And we're gonna see why in a bit. The short answer to this, we're gonna see the long one later, but the short answer to this is that by overwriting an information, we're actually deleting the possibility of restoring the original state of the system as it was on Monday. So by keeping the catalog continuously up to date with overwrites, we are kind of erasing all the history that the system see, during the days. For example, if I want to build a model that predicts price changes, and I did this, now it's impossible. Because for each and every one product, I will have only one price, in particular, the last price that has been sent to me, okay? And this is dumb, okay? However, we have a better design, which we're gonna present, that is gonna allow us, like Git does, basically, to have a full record of every event that has been ingested. And so if tomorrow we want to train a model that predicts the price of SKU 1 to 3, we're gonna be just one SQL query away to retrieve all the historical prices, like it was like stock price on Yahoo Finance, right? So I know this is counterintuitive, but this is kind of one of the key lessons that we learn, is that you never update, you never overwrite information in a data company. What you do, you always append new information to a stream, and then you build your views of that stream. So let's go back to some principles here before going to the actual workout solution of this problem. So what do we want from a data pipeline? Like, we want a bunch of things to be satisfied when we try and thinking about, what happens with data, from data that is outside our system to data that is ready to be fed to a machine learning model. So we want to be a reliable ingester, because every time we fail to persist data, let's say a catalog comes in and we fail to persist it, it's lost forever. We can never recover the past. We cannot travel back in time. We want a uniform representation of data. Again, continue with the recommendation, like system example. We want the catalog data and behavioral data are kind of in the same place. If data cannot be joined, data do not exist. Only data that is joinable with other data is actually useful. We want data to be validated, of course, so we want to make sure that people send us the right information. If not, we need to flag it. And we want data, which is, again, super important, to be replayable from the raw source. So we strictly separate the raw events that we receive, the catalog, from what we do, to transform them and make them available to downstream models. And finally, of course, we want something that is collaboration friendly. Since data is somehow at the core at every ML company, data is used for many, many different use cases, sometimes from people with different skill set and different price tags. So data is used from analysts for exploratory data analysis, used to people doing BI and data visualization to build dashboards to understand how the company is running, used by data engineering to build pipelines and tools, and of course is used by ML software engineers to build models, right? It's easier to work together if we all work with a shared set of tools that we all understand, because these people have very different skill and, again, very different prices, and we want to make sure that we sort of build on top of each other's strength. We don't want a guy with a PhD, in ML, doing too much, data wrangling of the raw source, and on the other side, we don't want to ask a person that is doing BI to set up an entire Python environment into a laptop to become productive, right? So we want to play into each other's, strength and make sure that everybody works well in harmony. So how do we solve this? Well, for ingestion and storage, we need to make sure that we run in auto-scaling and PaaS as much as we can. If we ingest directly data from us, we can find, for example, in AWS, a lot of solutions that were super well at reasonable scale. Lambdas are awesome, for example, to collect behavioral data. Firos is awesome to direct this data into a data warehouse. If you're doing and collecting data from other sources, solutions like Fivetran, for example, are amazing in actually helping you do that, in a very easy way. Then we guarantee that all data is joinable together by what we call the single source of truth design, meaning that all the data that is outside the system, like catalogs, that is inside the system, like the recommender system prediction in our example, ends up being in the same place. In this case, in one data warehouse. And then we make sure with data validation, the data is ingested in the proper way. We may send to our customer, for example, a library that we made, and make sure the data is sent in a proper way. So we can abstract away the complexity, for them. And of course, we write down what we call expectation after we ingest the data. For example, it's common knowledge that a pair of sneaker shoes cannot cost $1,000. So one thing we want to make sure once we ingest the data, for example, is that the column price, whatever column it is, never contains like a value that is over $1,000 or whatever it is for your use cases. As far as for the reliability, like work, we insist the raw data is stored in what basically is like an accounting ledger, like an append-only table. Where just raw data is stored perpetually as an immutable record of what happened outside of the system, in the system, like in the universe that is kind of important for us. And then downstream tables, that is what actually people work on, are just basically snapshots that result from taking this long stream of events and making pictures of it. It's kind of the same thing as like having a movie on one side, where all these, all the photograms, like all this, fine little history of what's happening in time with a movie, and then you extract, just snapshot of it that kind of capture a particular thing, a particular moment in the life of the company. Imagine we will always be interested in capturing the latest snapshot, as in the last, photogram in a movie. But again, by keeping the entire movie, so to speak, in the original format, we can always go back in different point in time and make sure that we can, we can work with that kind of seamlessly. And finally, on the collaboration side, if your team works with open source portable tools, for example, DBT, and language that everybody knows, for example, SQL, which is kind of the lingua franca for data wrangling and transforming data, you kind of build this cool, vibe into the team that everybody's contributing, building towards the same thing. And all the works that we do within each other is kind of like, interchangeable. So this is what is called modern data stack. So when we go from principles, okay, to solution to this principle, okay, to actual tools, implementation level, this is what, a modern data stack would look like. So we ingest, standardized, data sources with Fivetran. We ingest our own logs or data that we collect with, for example, Lambda and Firos. Everything gets logged to Snowflake, and then use DBT to generate tables for our use cases. So in particular, again, can't say this enough. If you remember our catalog example for which we opened, like the example in which we override fields in a catalog, we're actually proposing here a completely different perspective on what it means to do data engineering. So first, things never gets overwritten, things get appended to a table, okay? With, of course, some metadata like, I don't know, daytime type of events and so on, they kind of help us, working properly downstream. And then all the tables downstream are just nodes in a DAG. A DAG is just a, the recursivity graph. And it's basically this idea that transformation are a series of steps that can be replayed and run, in an exact series, okay? We're gonna see how does it look in practice with this kind of made up example, but to be, again, pretty easy to understand. Let's consider our, e-commerce use cases. So this is the raw events table, okay? This is a table that contains, all the events that, for example, we ingest here. In this case, we have product views, there is product that people click on, and cart views. There is product that people added to the cart. Again, if you're familiar with Amazon, that's exactly what happens on Amazon. So there's an event ID, which just identifies, what happens if that event is unique. There's a date time, which is when that event happened. There's a body, which is the raw event, like, is not shown here, but imagine just a JSON here containing, for example, information about which product was selected, or which category the user was browsing in, and so on and so forth. We have a user ID, anonymous, of course, and we have a product, an event type. Okay, so this table here, every second, every minute, every hour, just gets longer. This table never changes. Like, once a record is there, that record is never, ever changed, because that record just records what happens in a specific moment in time, in this case, to an e-commerce, okay? And since this records the past can never change. This is very important. But this table is basically never to be used in practice in our data company. What happens is that this table gets transformed to dbt, for example, into table that actually contain useful information for people that want to work with data. But these people do not necessarily need to know the raw information. This thing promotes, as we discussed, like an healthy division of labor between different type of people. So there are people that are closer to the raw data, that understand the raw format, and they're responsible for basic transformation of that raw format, something everybody can use. And there are people more higher up in the stack, abstraction speaking, that actually working with aggregation data. For example, people doing BI, people doing aggregation for country do not really need to know what is the raw format of a product data. They just need to know how to query, country data in a proper way to do a chart, right? And in this way, we kind of promote this healthy division of labor, where all the pipeline is written in SQL, so everybody can contribute and everybody can expect it. But then there's no need for everybody to know all the details. 1 second, there's a question. What's cost? We need to stream 1 million video day now. Later, we need to end the 10 million video day. We're gonna, thanks for, there's a question about costing. I think you guys see that. We're gonna discuss about cost in a bit. Thanks so much for the question. I won't forget about this. I got to talk about. So this is an example of a second table. So this table is exactly like the first table, but as you see here, we added one column through a transformation, which is the session. Session is a technical term in e-commerce that kind of is just a grouping of action that happens within 30 minutes of each other, okay? So if you're on Amazon and you search for something, then you go and get a coffee, and then you go back and you add that thing you search for to the cart, that's one session. But if you search for something, you go and have a walk, and you come back 30 minutes and 1 second later, and you keep browsing, that is a second session, okay? It's just a standard metric that is being popularized by Google Analytics as a way to analyze what people do in a continuous stream of events, okay? Session here, as you see here, session is a touch post data is ingested, right? Remember, we have a film. This is a movie where we keep on adding photograms. And then when we go back and analyze this, we can identify chunks of events that are basically contiguous, right? In this case, we have 3 sessions, right? The orange one, the red one, and the, what color is this? Well, the less orange one. So now that we have this table, for example, our people from BI can completely disregard the first table and can build nice counts for our dashboard. For example, it's an easy mental math to do that you can get these 2 tables, which are counting and aggregation for session and user, just based on this table here, right? So now just by knowing this table and knowing SQL, you can produce these 2 tables that, again, they can be used for different sorts of purposes. And finally, somebody that wants to train an ML model, they want to train, let's say, a session-based recommender, can actually build this even more complex table, which is the result of the sessionization table that we create in the first place, and the original table that contains the product, information that it was in the JSON in the original table. Okay, so now if we want to train a model that predicts what users are going to do in a session, which is actually an e-commerce real use case, it's called session-based recommendation, we do not need to know anything else that is not on this table. I hope you appreciate the powerful of this, because the person that train ML models just needs to read from this table directly, basically, and can train a model disregarding any other sort of information that is not relevant for him into this particular moment. And this is very powerful again, because everybody knows how this table is generated. It's generated through SQL, right? And this is the only thing that people building this model need to know. So if you picture this, in an extensive form, of course, you find out that this is a DAG. This is a direct acyclic graph. So this ELT is version and is replaced and is replayable, because every time you run it, you're gonna get a new result if the photograms keeps being added to the picture, right? And the other thing, which is what we mentioned, queries are built on top of each other. So you see here the dependency between some of these queries. So the dependency of some of these queries tells you two important stuff. One, of course, is what you need to know to build one of the tables, which is very important to run the tables in the right order. But the second thing, it also tells you what you do not need to know, to have tables. For example, when you're analyzing table number 4, you can totally disregard 1 and 5. And it's very easy, it's very easy to visualize this, right? So it's very easy to know that if you're working on table 4 for debugging, visualization, or whatever you're doing, you're not considering table 1 and 5 because they're conditionally independent from what you're doing, okay? So this is a very powerful design, and we're gonna see later. I prepare a second part, which is the ML pipeline. Remember, MLOps is MLSys is ML data pipeline, and ML pipeline equals MLSys behavior. There's a second session here on ML or Metaflow, which are also my friend Ville, ciao Ville, is also at this same amazing conferences. So there's an entire talk about Metaflow. So I'm not gonna bore you much with this. I'm just gonna mention a couple of things before going into the code, because there's an entire presentation about Metaflow. So ML pipeline needs to satisfy many of the same kind of things that the data pipeline needs to satisfy. So we want ML pipeline to be versioned. So we want every time we run a model building process to be able to run every time in a version immutable way. We want it to be replayable and easy to audit. We want it to be scalable, as in we want the model to run, irrespective of our data, and we want again it to be developer friendly. We want to make sure that everybody works with tools that we like, and everybody works pipeline without charge tool. And our choice of tool for this is Metaflow. You see here, this is a typical ML pipeline. 99% of ML pipelines that work with offline training are basically composed of this step in one way or other. And Metaflow is our way for organizing our script and orchestrating our code in such a way that this type of pipeline runs reliably at scale. Metaflow is really awesome. We cannot recommend it more. And there's a bunch of things that Metaflow allows us to do that we wasn't able to do before. And we're gonna see that directly when we're gonna see code in the second part of this talk. We're gonna leave you with this slide, so no worries. You can go through this, in your own time. So before starting with the code, let's introduce our repository. So it's called You Don't Need a Bigger Boat. I shared the actual link in the chat, and it's very important. Sorry, one question first. Metaflow is opinionated for AWS. Is there alternatives for other cloud platforms such as GCP? There are alternatives, and we're gonna discuss them, but I'm not sure they replace exactly what Metaflow does. Point in case though, Metaflow released a Kubernetes integration, which allow people to somehow have this hybrid experience and be a bit less tied to AWS. I don't know exactly what is the plan for adding more, Azure and Google and so on as a first world citizen, so to speak, of Metaflow. So for now, we're an AWS shop. So for now, our comment on this is gonna be just related to AWS. But thanks, very good point. So this repo, which we're gonna see after 5-minute pause, is not like a feature repo. It's not a repo that is intended for you to learn how to train a recommender system. This repo is the template on which you can build an entire data company at a reasonable scale. So it's a bit more complex than most, 5 minutes tutorial on Word data science, granted. But this repo can literally support a company that works with millions and millions of new events every day, and it's been tested at unicorn scale. Okay, so it's going to be a bit complex to go into all the mechanisms, but this repo, which is completely open and completely free for everybody, is literally a template for a company, not a template for a feature. So the problem we're going to solve today is intent prediction. Well, it's the problem that we mentioned, in the very beginning when we were discussing the Rakuten people. It's not an invented problem. It is a very interesting problem for people doing like ML in e-commerce. Second, is actually a problem that attracted, significant scholarly work in the community. So we're actually going to see a model that has been, published in a real scientific journal. The problem is, as we discussed, very easy to state. There's a user. The user is browsing through some product. In this case, there are soccer products, let's say in a sport apparel shop. We ingest, sessions with purchase event, a session with no purchase events, in our model, and we train the model to predict for a new user generating, product impression if the user is going to buy or not at the end of the session. So the target variable here is binary, buy or not buy, and the input here is the first K element of a session, right? And our goal, of course, is to be as precise as possible, even knowing that most people actually never buy anything. So there's a huge class imbalance here, okay? So the pipeline that we showed, so there's a lot of blog posts and tutorials online, and they're probably even better than than our repo in many cases. However, our repo is being built with a kind of different mentality in mind. So most tools focus on one tool at a time. If you go on a tutorial for Metaflow, for example, our tutorial Metaflow, we published a tutorial Metaflow like a year ago or something. It's just going to be about Metaflow. So you're kind of be left in the dark about, remember all the functionalities that you need to have that we described before. You're kind of left in the dark of how the other pieces of the puzzle fit together. Second, most of these, tutorials, for example, our own tutorial on Metaflow 1 year ago, tends to work in a toy war fashion. So they work with a data set that is kind of like made up, or it's kind of a Kaggle competition data set. There's not really representative of the world. So our repo is very different for these two reasons. Remember data ingestion, we discussed it, for how you ingest data to an endpoint serving prediction, so to model deployment. So you can go from the data to actual having real-time predictions with our tool. Like there's nothing you have to add. You're completely self-sufficient. That's why we said this is a template for a company, not for a feature. And second, we provide a data set, which is the data set we open source this year, which is really realistic and representative of many world use cases. The data set has more than 30 million of events, which means it's a mid-sized e-commerce data set if you work in e-commerce. But e-commerce is a very data-intensive application. Actually, outside of e-commerce and maybe advertising and stuff like that, most application will never see 30 million events, before months or at least weeks. So this pipeline that you can run for free on your laptop or in your cloud actually works at a scale that is bigger than most people at reasonable scale will ever find. And we can prove that we can train a model and deploy a model with this type of load just using the tools that we suggest. So the repo is complex, but if you can bear with it, you're going to end up with the backend of a company that can turn raw data into a realistic state-of-the-art model with basically no human intervention, okay? So I'm going to pause for literally 3 minutes right now because we're already after 1 hour since my Zoom kind of crashed for a bit. So we kind of lost a bit of time. I'm going to pause literally for 3 minutes to give everybody the time to collect their thoughts, ask questions, go into the repo and so on. And then I'm going to discuss, at 1:05, I'm going to start discussing the repo in detail. So we're going to go through the code and start analyzing what the code actually does. If you have questions in the meantime about the philosophical part, the conceptual part that we just saw, I'm gonna answer the question first, and then we're gonna go into the details of the repo and the code. Another question: if you guys want to reach out to me as you have more question you don't want to ask publicly or thing that pertains to your particular use case and so on. Super happy to talk to everybody. Like, add me on LinkedIn and kind of ask me your question there somehow. As I'm not on any other app, so it's very hard for me to keep track if you ask me questions specific, like like events app. Add me on LinkedIn, and and we can go through there. Okay. So there's a bunch of questions here, all interesting. The first one is, what are your thoughts on vendor lock-in? How big of a risk would be to rely on 10 different products? Well, I don't know if it's worth to rely on 10 products or one first. But the general thing is that there's something in between end-to-end platform, like, I don't know, Databricks, or even even more low code like DataRobot, and the bare bone infrastructure of big tech companies where everything is custom and so on and so forth. And this is a middle ground. Like, what we propose is a middle ground. What we say is that there are people that are sophisticated enough to not need or not like to work within the constraint of a pre-made data platform, and they want to pick and choose what are the best tools for their job, but they have not a limited budget or a limited talent to build everything from scratch to to their own needs. So the best thing for people at reasonable scale that wants to do cutting edge ML with things is making sure they pick their own product and the product that they like, and they know how it's easy, how it is to assemble it. Part of our evangelization job here is to demystify this idea that doing this is hard. I mean, doing this is hard if you don't know what you're doing, for sure. Doing this is hard if you have to find your way into 10,000 MLOps tool by yourself through as well. But if you have a bit of guidance, doing this is not particularly hard. And the reason why it's not particularly hard is, well, A, the community is amazing. There's a lot of amazing tools you can use. And B, at reasonable scale, infrastructure problem and somehow, reasonable by definition. Nobody's asking you to serve 2 billion users, overnight. But again, that's a strength, not a weakness. That means a very small team can produce incredibly delightful ML experiences just by knowing which tool to pick. Second question, what's your platform versus Amazon SageMaker versus GCP? I don't know almost anything about GCP. I've been an AWS person since my previous company, the one that I built, and now Coveo is AWS as well. SageMaker has basically no real role here, if not for deployment, because SageMaker is very easy. If you want to deploy something in autoscale and your model is on S3 because you use Metaflow to version the model, which what we do, SageMaker deployment is one line of Python. So this is the reason why here SageMaker is used. But again, we can disagree on specific box here. You see the box here, right? You can disagree on specific box here, specific logos. But at the end of the day, you need to fill all these pieces if you're building a stack. The cool thing about this stack is that it's already built for you. It's already been tested. But if you want to, there's a million companies doing model serving. You can substitute SageMaker with whatever you want. And for the question about serving, SageMaker is exposed with a Lambda. So if you go and look at the code, SageMaker is going to be an internal endpoint for AWS, and then there's going to be a Lambda which kind of provides you this interface with the outside world. Okay, so hopefully I answer all the questions. So back to the repo, which you hopefully see my screen. So this is the full pipeline. We provide two versions of this. Okay, so there's one version of this which is just runs on, which is here is the local flow. Okay, which runs on just locally with Metaflow. So it is way less dependencies. And what happens with that pipeline, we're gonna see that here, is that all the steps from raw data to basically shipping the model happens as Metaflow step. If you're not comfortable with all these functionalities and all these ideas, I strongly suggest to start from this because the barrier to entry is basically inexistent. You just have to basically install Metaflow in your AWS account and download the data, and then you can run it with one command. You can literally run it with one command, okay? Once you're comfortable with how the pieces fit together, what we suggest though is not to run everything as a thing, to run everything with a more general orchestration pipeline, for example, Prefect or Airflow, for example, and have Metaflow just taking care of the ML pipeline part, okay? This is especially true for B2B companies. Why? Because since we have 500 clients, like we're not Amazon, we do not own an e-commerce. We provide hundreds of e-commerce with APIs. we need to decouple data validation, data wrangling, data transformation from modeling code, right? So we cannot really put a lot of specific about data into the ML pipeline, because the ML pipeline runs for hundreds of different clients and different catalogs. Okay, so we want to keep somehow the two things separated. So a lot of the data work that is common to all the clients happens in the DBT stage, so to speak. You see here, and the ML pipeline is more about feature engineering, model training, hyperparameter optimization, and so on and so forth. Okay, but of course, there's people that use Metaflow as an orchestrator. I mean, you can totally think of reducing all this pipeline to a Metaflow pipeline and just run it like that if you want to start simple. Again, you can do that with the local flow. Okay. So the other thing that I want to mention is, well, actually show you. So this is the remote flow. So this is when everything happens. Okay. And this is, this nice graph that has been exported by Prefect that shows you, how things actually work in this in this pipeline. And if you go into DBT table, you can find all the transformation. Remember what we discussed, right? There's a row table and there's a transformation. They build this event in such a way that it can be used from the outsourced system. And you can inspect that instead of the made up table on my slides. You can actually inspect them, right? And you can actually make sure that you understand that a simple SQL query like this one, that is what you need to go from raw data, data that is ingested, and remember the JSON body in our example, to tables that everybody else can use. So if you want to see a real example of what happens from real raw data to transform data just using DBT, the remote flow folder into this repo is your friend. Spoiler alert, we're actually going to release a new open source repo that focuses on ingestion. So they focus on ingestion and transformation. That is going to be even more detailed on how you can operationalize this type of append strategy that we described. So follow us on LinkedIn, because we're going to do that in the next month or so. If instead you're interested more in understanding Metaflow and how the pipeline part works in the ML, you can check, for example, this file. It's called cart baseline flow, okay, which is basically gonna show you how you can run a Metaflow pipeline ingesting data with realistic constraints and realistic models, and then validating data, prepare the data. If you see here, every one of these functions, which is a step, if you know Metaflow, is a node in this DAG, is doing exactly what we discussed. It's validating data, it's preparing data, it's training the model, and so on and so forth. You can see here how handy this is, right? When you train the model, you need a lot of computing power. So what you do is that you request a GPU from the cloud, which you obviously don't need when you just get model config or when you prepare the dataset, right? So this is the power and the magic of Metaflow, abstracting away computing so that you can pick and choose for every part of your pipeline, where do you want your step to kind of get executed, right? And then finally, we discussed this with SageMaker. So since you can basically serialize to S3 somewhat very easily, you see here, this is using the S3 client from Metaflow. You can save the model at the end of your training routine as an S3 artifact. Then you can just deploy it. This is just a convenient function that use Boto3 Python API to deploy a SageMaker endpoint to actually ship the model. So you can be sure when you train the model, you test the model, you make sure that the model is ready to go in production. 3 more lines of Python will actually deploy this model. And then, of course, if you have a Lambda in front of it, you can use serverless or CloudFormation or whatever you want to kickstart that deployment process as well. So if you're interested in more of the data ingestion part, look at the remote flow and the DBT folder especially, okay? If you're interested in the ML pipeline, look in the local folder and especially, the file name flow. If you follow this instruction and if you follow our lead, you're gonna have a system that's gonna be able to run state-of-the-art models in production, with a sufficient latency for recommendation engine, starting from raw data. And you do not need to maintain one single piece of infrastructure. all of this thing here run either automatically in the cloud, for example, with AWS, or run through other PaaS services that you can pay, and they're very cheap. Like Prefect Cloud, for example, is very cheap. Comet and Weight and Biases are pretty cheap, and so on and so forth. So the entire point of this diagram is showing you that you can run a backend of a data company shipping state-of-the-art machine learning models without any MLOps person. So all your job is to actually producing value for the company, is to understand your data, make sure the data works fine, make sure the model works fine, and none of your duty is maintaining or scaling infrastructure. And we think this is pretty powerful because it's the first time in humanity when companies that are reasonable scale, with a small team, can actually build incredible ML products just by leveraging this type of reasoning. Do not maintain or do not deploy anything that somebody else is maintaining for you, and just focus on the business. Like you focus when your expertise in domain logic, business logic, ML training, and so on and so forth. Again, this is not the only recipe, but this is one recipe that works, and it's open source and it's free, and it comes with a lot of more materials that we cannot discuss today. Like there's a paper here if you prefer more scholarly version. There's my talk at Stanford, 3 months ago if you prefer, like another conceptual overview. There's a blog series on Toward Data Science if you want to have a longer explanation of all the things that we said today. Okay, and this repo is actively in progress. If you find this useful, so if you find this talk useful and this repo useful, if you find this idea thought-provoking, we ask you to share this repo and to add a star in our GitHub so that the repo gets even more known and more shared, and then more people can actually try it out and tell us what they think about it. If you try it out, please reach out to give us feedback, because what worked for us as mostly an e-commerce shop may not work for use cases, and we want to learn from you. We want to hear how much of this pipeline is actually universal, as in everybody can use it, and how much of this pipeline they need some trimming here and there, or some new tools here and there to be even more general. But yes, but if you like it, please add a star to our repo. We'll be very grateful for that. So back, if there's no question on the code organization, on no other question on things, I'm gonna answer the question about cost that has been raised before concluding the talk for some more questions. So somebody asked before that they need to stream 1 million videos per day, and later on they need to stream more. So I don't know about the streaming part of it, and there is technically not an ML concern because it's more of a serving, buffering kind of concern. But we run this pipeline with millions and millions of events per day successfully. And again, if you download our dataset and you run this pipeline, you will realize how effective this pipeline is training models with dozens of millions of events. Okay, so this is a test you can very easily do on your AWS, on your own Snowflake, and verify how much you pay for that, and verify if that's okay. In our experience, at reasonable scale, it's almost always worth the money to pay Snowflake, AWS, whatever, instead of going for an infrastructure as a service technique that requires people to maintain. People cost way more, especially in this market. People that are very good at this job cost a lot of money. They're very easy to retain, as in if you give them boring job like maintaining infrastructure, you're likely to lose them. So there's a lot of HR hidden cost there. And it's very hard to predict how people scale. Well, it's very easy to tell you how much this thing is gonna cost if you increase 10x the amount of data. You just have to sit down and multiply, a bunch of invoices. It's very hard to predict how much your team. It's not that people are not important, but if you can keep the team small, communication and the type of work they do will actually benefit a lot in our experience. Like starting an ML platform by hiring dozens of people that have done that before and ask them to figure it out is a recipe for disaster. Our suggestion is start with a core group of 2-3 people that understand this end-to-end, that have done this end-to-end, that understand data ingestion, that understand data transformation, that understand ML training, that understand serving, and have them build a system, for example, maybe this one, maybe something similar to this one. They build a system that other people can build on, okay? Because if you only have data scientists that the only thing they do is writing models on notebooks, then you have 30 expensive people that the only thing they do is creating more confusion. And remember what we said, 87% of projects never go to production. And that happens all the time in organization, especially in the one that are not super mature. Do the opposite. Start small, invest in a good infrastructure, in a good developer experience, and then scale up the team as needed. Because you will find out, and I personally guarantee it, that if you build the right data system, you're gonna need way less people than you thought you will need to achieve the same ML capabilities. You find out that you can, produce ML cutting edge model, publish at top conferences with a team of a very, 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 very few people, okay? So the key takeaway for today, and then, answer any question you may want, is that, well, you can indeed run terabyte scale workload without any explicit infrastructure work. Our repo is actually, the proof of that. You can download it, try it out, do whatever you want with it, and please, again, leave some comments, leave some feedback, share it with whoever you think may be interested in learning about this. 2, not every tool has the same importance. In particular, tools that are like computation heavy are, of course, playing a more fundamental role into this pipeline than other tools. In other words, it will be much harder for us to replace Snowflake than to replace, I don't know, like a Great Expectation. Of course, what we present is very easy to extend and very flexible. You can add a low-code library in Metaflow if you don't want even to do model training yourself, or you can swap in different SaaS provider as long as you know how they fit into the overall puzzle. But finally, which is what I just said, remember, it's still hard for the field to understand the peculiarities of AI companies as compared to traditional SaaS companies. Everybody agrees AI companies are slightly different, but nobody really agrees why. But one thing is for sure, in 2021, which wasn't true in 2007, in 2021, small teams can do great AI things thanks to this thriving ecosystem of tools and idea and best practices that are kind of starting to form, in this MLOps thing. So I'm gonna skip again some slides. And so what is the future for us at reasonable scale? Like what if it's true that we prove, quote unquote prove, that engineering is not a barrier for reasonable scale people to do ML at the highest possible level of the field, what else can we do? Well, there are many other things that we can do. We can contribute data sets, right? Remember, data sets are a big problem. And we open source a big data set. We contribute code so that people can actually use it. And then, of course, we keep on publishing our idea. And typically, if you read about our papers, most of our papers are actually reasonable scale papers. There is a paper suggesting techniques that works for, every kind of shop, every kind of company, not just if you have a YouTube recommender. We're kind of not just showing, we like to see what Roger Federer is doing while training, but most of our papers are actually about a normal tennis player training and some tip and tricks that everybody can use. And we will continue to do so in the near future. Thanks so much for being, with me today. The slides are gonna be available for sure. I'm gonna open source them. I guess the video is being recorded, so that's gonna be open source as well. Any question you may want to ask, I'm here for you guys. So Matthew asked, any recommendation for maintaining security and regulatory compliance when working with sensitive data across many tools and platforms? Very good question. So apparently, and I discussed this with our friends at Netflix. So there are ways in which you can work, for example, with Metaflow, even in a very high sensitive environment. And that typically the data that comes in, and then data that gets anonymized, scrubbed, or redacted for things that happen downstream. So while we do not have, or we did not publish yet anything that is heavy on the side of being super, regulatory compliance, we believe that the same recipe of making sure the data is kind of processed in a version and compliant way in one side, and then everything else downstream feeding from that, clean data store will apply to these use cases as well. So the more care we take into preparing data ingestion and preparation, the better everything is, including security and compliance. So Diana is asking, in this pipeline you have, how do you think DVC can contribute? So I never use DVC myself, but I've heard only great things about it. In our case, since we're a Metaflow shop, we kind of get versioning of data automatically by using Metaflow. As in, every time we want to snapshot any variables, we can just do self.dataset, and Metaflow will snapshot exactly that dataset that gets fed into that model at that moment in time. So if I want to go back and see what data went into which model training, I can always do that. Plus, having raw data and version transformation like in DBT, I kind of do not really need to, again, keep track of that because that is already version for me. So I'm sure there may be a role for that. For us, it's not obvious, as in all the data versioning stuff that we need to do are kind of taking care between DBT and Metaflow. But I'm sure for other users that may not be true. Oh, Amar, for example, just comment, DVC pipeline could complement Metaflow, and I'm sure that's a very good suggestion. But for us, we just never encountered the problem of data versioning on top of what we do with our usual, DBT plus Metaflow flow.
Okay, thank you very much, Jacopo, for such an interesting talk. I had already left a star on the GitHub repo, and I invite the attendees to do the same. It's such a great material. Thank you very much. Yeah.
Thank you very much for inviting.
Yeah. A brief reminder to the attendees, if you have purchased a summit ticket and are joining us for the talks on November 17 and 18, please look for an email from Hoping in your inbox today or early tomorrow for you to register in the virtual conference platform. And thanks again, everyone, and have a nice day.